Hello, everyone. Today we are honored to be speaking with Dave Hughes, the CTO of Novsound, an award-winning Scottish sensors company utilizing thin film processes to eliminate conventional limitations in ultrasound sensors. Dr. Dave Hughes is the founder and CTO of Novsound. His background includes degrees in both physics and engineering and over 10 years of ultrasound research experience. He is now a high-growth entrepreneur overseeing the technical direction and vision of Novsound, which has rapidly revolutionized industrial ultrasound technology, which has remained largely unchanged for 40 years. Novsound was founded in April 2018 as a spin-out from the University of the West of Scotland, where Dr. Dave Hughes invented Novsound's core IP. Under Dr. Dave's leadership, the company has quickly grown to become an award-winning global business, manufacturing ultrasound sensors for a range of industries, including NDT in oil and gas, aerospace, and semiconductor markets. Welcome, Dave, to Floodlight Software's NDE 4.0 podcast series, which poses 5 questions to an NDE 4.0 expert.
Hi there, and thank you very much for having us, having myself.
Great. Well, it's very exciting to have you on our program today. I'm really interested in the use of sensors for NDT and the future potential of continuous monitoring. So I'm really excited for this conversation today. How about we start with a basic question to start with. Question number 1 for you is, what are the different types of sensors that can be used in NDT? How do they work, and what data can they provide?
Okay, so that's a very wide-ranging question, and in non-destructive testing, there's a huge array of sensors that are available to basically do what they say on the tin, non-destructively test an object. You don't want to break apart a pipeline in order to assess its health. So you get electrical sensors, such as using eddy currents that generate eddy currents in the object, pick up reflections of these as they travel. You get optical sensors, your digital cameras, visual inspection based methods, both inside and outside using borescopes, etc. Chemical sensors are used a lot in the corrosion industry to look at the chemical changes of a material as it corrodes or erodes. And then where Novsound tends to be based is in the mechanical or acoustic sensors. So mechanical sensors could be used for vibration detection. So if when you're monitoring a part or a bit of machinery that's moving, if it's working properly, it will move in a very constrained rhythmic manner. When issues or problems start to rise, you start to get vibrations that are away from the normal signal, and these sensors tend to pick them up. The other type of mechanical wave aren't the mechanical waves that you can feel or you can observe or witness, but they're more above a certain threshold that turn into acoustic waves. And an acoustic wave is just a mechanical wave that propagates through an object. You get acoustic emissions. So if a pipeline or a part fractures, it will send a very high frequency sound that you may not be able to hear with your ears, but it's able to be detected by an acoustic MEMS microphone. That's one version of an acoustic sensor. If you go higher in frequency, you start to get into the ultrasound domain, and that's where Novsound operates. We concentrate on high frequency ultrasound sensors, and these are active in that they will send an acoustic pulse into an object. So it's not detecting acoustics that get generated through fault. We are actively putting sound into objects and listening for the echoes coming back. And from that, you can measure and build up a picture of structural changes. And these might be due to corrosion, erosion that give rise to wall loss, or even the internal buildup of waste products, for example. You can image these with ultrasound. And that's ultimately what Novsound do. We create sensors that use ultrasound to measure these structural changes.
Oh, interesting. So how, when you place them on, say, a pipe or something, how far apart do you have to place them, or what's sort of the optimal, is there an optimal range?
That really comes down to what you're trying to look at. And a lot of the time through the history of NDT, the NDT engineers start to understand where problems are going to arise. For example, elbow joins are more common to be corroded than a straight flat part. Okay. So with our sensors, you would tend to place them at the parts that are known to corrode or to erode, so you can get a measure of how fast it's happening or if it's happening at all. There's lots of
Right,
times
right.
where you may believe that corrosion is happening, shut down a pipeline in order to properly inspect it and find nothing. It's absolutely
Mhm.
healthy. So why did you shut down and potentially risk losing, a large amount of money for this downtime?
Mhm.
Novosync solves that problem by allowing you to continually monitor the part without shutdown.
Interesting. Fascinating. So let's move to our question number 2 for you, Dave, which is what challenges and or hurdles need to be overcome in order for an NDT company to successfully deploy and use the technology?
So I've split this kind of train of thought into two parts, and you can always, as a physicist, as my background's in physics and engineering, I really want to solve the technical challenge first. That's where I always jump
Mhm.
to. Ever since I started moving much more into business and setting up Novosound, you realize that there are no real technical challenges left. It's only commercial challenges. So
Right.
on the technical front, and it's the part that Novsound has solved, is how you get a sensor to be simple enough that you can place it in any environment, low temperature, room temperature, atmospheric, right up to very hot, and still measure the mechanical change that you want to monitor. So the real kind of technical barrier to continuous monitoring is having the right thing to measure that enables you to assess the structural health of the object that you're looking for. Once you have that, you move right into the realm of the commercial problem.
Mhm.
What's the return of investment or the economic impact of investing in hardware to monitor this versus sending in the rope access or the human engineers to do the
Mhm.
inspection as well? So, should you invest $100,000 a year for a section of pipe that will give you, if you shut it down, $1 million of loss for the time being down? So you have to balance these up. And of course, you might spend $100,000 installing sensors on a pipeline that just doesn't corrode as fast as you think it does. So you wouldn't
Right.
have spent the $1 million, or you're not saving the $1 million a year because there's no problem. You don't know that until you get started in a lot of
Okay.
it. But there's a lot
So
of
it's a
intuition.
learning experience. It sounds like it's a
Absolutely.
learning experience. Yeah.
Yeah. So that would be the third category problem: technical, commercial, and just luck. So
Yeah. Yeah, the continuous monitoring side seems really interesting to me because um, the idea to me is that you can be a lot more proactive about problems versus waiting for them to happen and then having to fix a problem that's could be really costly to clean up.
no, absolutely. It's all about increasing the flow of data to allow you to do the predictive analytics to be much more efficient and economical with the cleanup effectively. Oh,
Yeah,
and
yeah,
even if you can prevent in the first instance so that you don't have the cleanup.
right, right. That's really interesting. Let's move to question number 3 for you, which is what are the benefits that can be achieved through continuous monitoring and how long until those benefits can be realized? Kind of to point to your ROI question.
Yeah, exactly. So the ROI really stems from what is it that you're wanting to monitor, and what's the, if you don't monitor it and it goes unchecked, how much is it going to cost to put it right or to ignore it? And sometimes
Mhm.
ignoring it can be much, much more catastrophically expensive than just monitoring it and making sure it's okay. So by increasing the flow of the data, you move away from a situation where you may only have a data point every single year, and you have
Mhm.
to infer or work out what happened to get from the reading in December 2018 to the reading in 2019, and then you're not going to get your next data point till 2020. You're in a black box situation that you may find in 2020 that things that were okay are now not, but what's happened in the middle?
Right.
So when we are talking to our clients, the main colouring in of this idea is to basically say, let's turn the light on. Let's get rid of the unknown of the sampling between 18, 19, 20, and you end up with a regular unmanned inspection going on to allow the flow of data to increase, to allow you to have much more economical planning and implementation of the traditional NDT in the first instance. If you, as we go back to the idea of some parts just won't corrode as fast as others, if you know where you have to put your resources at the small window of time that you have to go off and do your inspection, the economic benefit starts to multiply, tenfold, hundredfold, versus doing nothing and just staying with the conservative way of doing it once every year, once every 12 months. If you're lucky, you might have an unplanned downage or outage, so you can go in and do an inspection, but the reason for an unplanned outage is going to be kind of
A
perhaps what
failure,
just
right?
exactly, it's a fail, something's gone wrong to enable that
Yeah.
increase of data. So let's try and increase the data without relying on things going wrong.
So how much data is involved in a continuous monitoring system? You talk about exchanging one data point a year to how many data points? Is it, a data point once every hour? Is it once? I'm sure it's probably settable, but what do you think what's typical, I guess?
So this all depends on the application or the object you're trying to monitor. For example, in heavy pipe work, we're talking like duplex steels or highly corrosive pipe work, you might only get a material loss of, a millimetre a year or so in terms of your wall loss. And the time in which, so the time in which you have to monitor it is going to be very slow. It's not going to be a real time, like a video feed. It'll be like watching paint dry in some respects.
Exactly.
But then if you go to a point every week, as opposed, so if we say we don't need it every minute, we don't need it every hour, because these are going to be micrometers of wall thickness changes that you may not be able to see, and then it's a lot of noise. If you go to every week, you may start to see a very slight change. Every month, that's you're only getting 12 extra data points a year. So there's always going to be a balance based on how fast you expect from your existing readings that you're going to need to sample. Oversampling a lot of the time can be useful in order to get a better picture, but there may also be some cases as if you were to jump into the deep end and say, right, let's install these sensors, let's take a measurement twice a day for the next year, and you actually see a lot more stuff going on than you just did not expect, and it becomes actually quite a worrying affair. There may be decision makers higher up the chain that do not want to see that kind of level of unknown, for example, in safety critical environments in aerospace, oil and gas. What we want to do is really work with those decision makers in the safety critical environments to understand what data is needed to make it as safe as possible without getting over the top.
Right.
In terms of unearthing faults that aren't real faults, maybe false friends almost.
Yeah. What kind of do you get any pushback from companies? In one of our previous podcast sessions, one of the things we talked about was this, this sort of interesting dynamic between, obviously the whole point of the systems that we're putting in place is to increase safety and integrity of infrastructure. And obviously there are certain regulations that a company needs to adhere to. An asset operator needs to perform a certain amount of inspections to maintain the safety of their systems. What you are offering is much more information than they can get from human inspections, right? So is there any pushback on, because one of the things that we talked about was in a different session was that, if you actually learn that there's a problem, let's say you're only required to test a particular component once a year. If you decide to test it every month, and then you learn of a problem, 2 months after your last test cycle, for example, you are obligated to fix it, versus previously, without having that knowledge, you're only really obligated to look at it in 12 months time. You may not have seen the issue. You know what I'm saying? There's kind of that balance between wanting to do the right thing, but then also being required to do the right thing because you have the information, whereas you might previously not be required to have it.
No, absolutely. And that's what I was touching on just before, in that this move towards continuous monitoring, or NDE 4.0, NDT 4.0 as well, it increases the amount of insight and data or information, let's call it data. I always think is the raw form of information. If you took a sensor reading every minute for a year, you'd have a lot of data, but you might not necessarily have a lot of information. So let's think about, in terms of information, when you have so much more information, things will come out of the woodwork that you might necessarily not have known till later. So it does
Right.
increase the workflow to an extent. This is how I kind of see it kind of disrupting and also revolutionizing the NDT service parts. This is still the manned part, because NDT services, as well as going out and doing the inspections, that feeds the maintenance segments of the market as well, where there's the actual repairs that have to be done. So in some respects, it will generate more work in that part, which is good. That might offset some of the decrease in the activity in the services. But at the same time, some of these challenges that will get unearthed through the increased information might not necessarily need to be acted on. So in the first period, there will be a lot of false positives or false trends coming up that will get fixed, and we'll end up with some really great improvements to assets. Other parts will be disrupted, repaired, but not necessarily going to be causing a problem later on, just because the sampling rate is so high. As you move into the different phases and get more deep into NDE 4.0, the sampling rate will decrease, because we'll understand more about the trends, we'll understand more about what the predictive analytics actually tells us. So you might find that for example, in corrosion, you can get situations due to the chemical balances of the material loss where it happens very, very slowly over a long period of time.
Sure.
But then because of the makeup of the cap, the pitting that happens inside the pipe, it suddenly just accelerates. And it's the chemical process that just tips over, and all of a sudden you've got a decrease in the wall thickness very rapidly. So you move away from the linear wall change right to a non-linear wall change that can make problems happen much faster than you thought. If you're only taking 2 data points, one at the start of the year and one at the end, you'll only see the end point of that fast problem arising. If you took a data point every month and you've got 12 data points, you then should be able to see like a nice linear change in the wall thickness, and then a drop down, and catch the drop down before it's going to burst through the wall to an extent.
Right.
However, if you concentrate on that linear regression to start with, you might get into a false sense of comfort, or you might repair it earlier, causing one of these unplanned downtimes where you might have had another 6 months to go just before it was actually needed to do that work. So that kind of brings us into the challenge of when is the right time to get on board with starting to collect this data, because you will have a type where there's a lot of redundant sensors, a lot of redundant data points, and a lot of activity that will be quite costly. The benefit of this whole continuous monitoring has to be looked at from a long-term vision point of view. There's the pain now, and the pain being the expense and the capital that needs to be invested to put the sensors out there, so that in 2 years, 3 years, 5 years, up to 30 years, you start getting to a point where you're inspecting parts where you haven't invested in putting the sensors on those parts, and it starts to become much more automated. You're starting to inspect uninspected parts as well. But it's such a long transition that trying to convince the industry to jump in now and spend the money now to save the money later in these are going to be long contracts that are going to be outside the time scale of employment contracts. So does one person want to invest in something now that's going to save their predecessor or their successor who gets glory? It's so that's one of the biggest, going back to what's a commercial challenge in terms of, and it's the long-term vision. We're not talking about tomorrow, we're talking about a year.
You can see that there's a lot of planning involved with a system like this. Let's move ahead to question number 4. This talks a little bit about artificial intelligence. What's the relationship between continuous monitoring and AI? What types of AI algorithms can be used with this type of data, and what results are companies looking for?
Okay, so AI, artificial intelligence, I always look at that as just being a very complicated way of describing standard statistics or standard trend analysis, and everybody does it. We already spoke just a couple minutes ago about looking at a line that's decaying. We do that by visually looking at a graph and making up some intelligence. That's, at the end of the day, the simplest form of that is linear regression. So when you were in your school. I don't know if it'd be elementary or the other types of schools that they have in America. We have primary, secondary, etc. When you're in secondary school, you get taught how to fit a line to an Excel curve. And at the end of the day, that is a simple form of AI because it can tell you what's happening after the data points of your graph finish. Anything else in AI is just built on top of those principles. You have some data, you fit a trend to kind of point towards where the data is going, and you make a decision based on what that is. In order to get to that point, you have to have enough data points. You can't fit a line over 1 point. You can't fit a curve over 2 points. You need more data in order to get the right trends and the right shape of the trend. So before you even get to the AI, we always see it as like a four-step process almost, in that you sell the sensors to get the data points there, and you collect information from them using manual inspection, rope access inspection. Then you collect more of this by automating that with a data logger. So you're starting to flow the data into a database. AI then turns on at that point, and through the uses of the linear regressions or k-means analysis or random forests, these are just basic statistical ideas that have been used for hundreds of years, or maybe not hundreds of years, but tens of years, let's say, to create reports. So you're now selling reporting, you're now selling what's known as the monitoring part of continuous monitoring, the predictive analytics. When you start becoming much more complex in the AI and you move beyond the statistics, you get into the kind of markets the IBM Watson sell into, or edge processing, deep dive. And with these kind of really advanced neural networks and beyond, you're now moving into the future predictive analytics. There's a lot of buzzwords. I realize I just threw a lot of buzzwords out there, but at the end of the day, these are just complex terms for fairly simple statistics. The complex part comes from the data that's fed into them to train the models. You can only train the models if you've got a history of data to build upon. So Novsound really bridges that gap between the world at the moment where there's sparse data points,
Right.
the cost effectiveness of having enough data points, to moving it into a place where it is cost effective to have a large number of sensors out there feeding data into these models. So in the future, you can start reduce the number of data points and move to a point where there's trust in the AI signals and AI reports that are coming out of it. That when you have, say you have 3 or 4 assets, pipelines, let's say, that are all very similar, same operator, same transporting the same materials through them, and you invest in year 1 on the sensor system along 2 of the pipelines, and maybe half of the third, so you get 2.5 pipelines that have lots of data on it. Over the years, you collect lots of information through the sensors. You plug them into your complex neural networks and your AI algorithms that your boffins have come up with. With enough data, you're now, just through that investment, that capital investment, you're now monitoring the 4th pipeline without a sensor going near it. Right. And I really see that being the power of this kind of move into NDE 4.0, NDT 4.0, where when everything's designed on computer and built reproducibly and it's all at scale, the amount of errors or changes part to part should be minimized. Right. So if you inspect one, you're right into that realm of statistics and predictive analytics that you can start to monitor things that haven't been monitored. But to get to that point, you have to invest in monitoring a lot of stuff right now. Right.
So I have this vision that I call my NDE 4.0 nirvana, which is a world where catastrophic, failures don't happen. And that's because we're proactive by using these technologies to predict when failures are going to occur. And, to me, that's when we talk about continuous monitoring systems and making this type of investment, that's really the world we're looking at. And the comparison and cost, you talk about the investment that companies have to make today. I wonder how much they anticipate or, kind of put in the coffers for a potential catastrophic issue that they might have to, resolve. And those are incredibly expensive, right?
So yeah, really expensive problems happen in an instant. And we've all seen them in the newspapers over the years, and we're probably just around the corner from the next one. a lot of the time they don't want to be able to put a cost on it because that kind of gives into predicting that it could happen.
Right.
Whereas if we can, with Novosound's manufacturing techniques, really bring the cost point down, it's less of a challenge to actually, it becomes the smoke alarm in your factory almost. It just, you forget it's there because you've not got a bill for $1 million a day to keep your factory safe. It's less than that. So it becomes just part of the running cost. It becomes in with the bricks and mortar of building a facility, building a pipeline. And through that inherent invisibleness of the continuous data and continuous monitoring, your safety improves. You've disrupted an industry. You've made that service segment smaller. You've increased the equipment segment, which is good for hardware manufacturers like Novosound. But through that, you've increased safety, which is the number one priority.
Right, exactly.
And through the safety, you're now much more efficient because you've not got these massive outlays of insurance payouts and all the other kind of costs that come with a disaster.
Sure.
And you're efficient because people are going to work and coming home each day in the same status that they went to work in the morning in.
Yeah. So it's been a really, really interesting discussion so far. Let's go to our last question, which I think you've already touched on quite a bit. So, but let's see what additional information you can provide for us here. The last question is, how does an NDT company get started using sensors and set a path for moving forward?
I think simply they give us an email and then we'll see what we can do for them. without it being a sales pitch, it comes down to that process that we've been really developing over the last 2 years as a company. We're a very new company and not many people have heard of us, but hopefully over the next 12 months that changes. We've just appointed a new chairman to the business. That all got announced actually just the day before yesterday, so this is good timing. We've got our new chairman's a person called Dr. Derek Matheson, who was the Chief Marketing and Technology Officer for Baker Hughes, which is one of the biggest NDT companies in the world.
That's right.
He's recently left Baker Hughes, and the first appointment he's made is to become the chairman of this little company from Scotland. He's originally Scottish, so there is a link there. So we're really excited with what that brings. He has a deep interest in the data and the digitization of metrology, which is what we do, and that's what's attracted him to work with us. And we're hoping with him bringing his expertise from that field towards Novosound, we'll really be able to make what we've spoken about so far into reality. With
so maybe Baker Hughes will be one of your first customers, right?
We hope so, and if it's if we're selling more than yes, absolutely. That's it's great for a 2-year-old company like us to suddenly be on that map, which is just great. But to answer the question, it is that 4-stage process that we see companies need to engage with now to reap the benefits later of getting the sensors bought, even if they still have to do manual inspection. By buying the sensors, fitting them to the asset, and leaving them there, you reduce operator error, so your data gets better. The information and the measurements you get now are better through a fixed sensor, and you can have as many of them as you need because the cost-effective point is there now. You then upgrade that and you get the data loggers, and there's data loggers that are off the shelf, so that's not new technology. That's a simple investment. You then move into the proper data analytics and the statistics and the artificial intelligence by adding the reporting to it. And again, Novosound provide that, but then there are industry experts, consultants who can take the data and write reports. So it can be quite a nebulous kind of way of doing it almost. It's not a defined package that fits all industries. Wind turbines will have a different system to oil and gas or to aerospace, but the core experiences and expertise that level 3 ultrasound or level 3 eddy current or level 3 NDT in general inspectors will have all tap into this. It's just a case of digitizing it and moving forward with it. They can't digitize it until they have enough data to start playing and, as we say, inspect the parts that they're not looking at.
Right, so just get started with what you can and start collecting data.
Yeah, and who knows what system we'll end up with in 3 years, 5 years, 30 years. If anything, Moore's Law has told us we cannot predict what's going to be around the corner. And if anything, the COVID pandemic tells us you can't predict what's happening in 6 months, let alone. And I'm hoping in a small sense that the COVID pandemic will make a lot of the operators of these pipelines or factories think about how can they do their inspection without putting a whole bunch of people together on a cramped boiler or a cramped pipeline in order to do the inspection. So you're not only increasing the safety of those who work in the factory or in the plant, you're actually improving the safety of your NDT crew as well. So they're
Absolutely.
so multifaceted that it's the right time now to start, but who knows where we'll end up.
Yeah, I agree. It's very, very exciting time in the world for sensors and NDT. And I thank you for all your great information today. Thank you for being on the podcast today, Dave.
Thank you for having me.
You're welcome. So I feel like this emerging technology has the potential to greatly disrupt the market and improve testing services. So thank you, listeners, for tuning in today. If you're interested in learning more about Dr. Dave or Novsound, please look for links to appropriate websites on our podcast webpage. Thank you very much.